Hello, everybody. How's it going today? My name is Connor, and today we're going to be talking about my new project I've been working on. It is a custom architecture designed by hand for fun and my own education. CPU architecture. Um, it's it has its own assembly language. It has its own machine language. It has its own binary format right now. It has its own assembler, and it has its own virtual machine that I've been writing. Um, and this is all created by me. Um, so I'm be doing it just for my own like education on how CPUs work, how compilers and assemblers work. It's been very educational for that purpose. Um, and today I just want to talk about how it works and just kind of geek out about it for a bit because I've been working on this for a few days. I am still planning on working on my operating system k4s. But I decided to take a little detour and work on this since I was getting a little burnt out from the operating system project. Um, so this is kind of like something similar along the same lines where it's like um, it's a low level, very on the metal kind of project. Like the operating system was a no STD Rust project, no standard library, no very much like an embedded project, even though it was just running on an emulator. But um, so um, yeah, so let's go ahead and talk about the architecture for this video, and then I'll get into assembly language a little bit probably. Like this is an example of assembly language program that I've written in my own assembly language. Um, but for now, let's just talk about how the architecture works. So, um, if you don't know anything about how CPUs work, I'll explain a little bit of it in this video, but um, I recommend that you look up some resources on like how, like simple processors like the 8086 work, because my architecture, it's called k4s, by the way, k4s. Um, so k4s was inspired a lot by x86 and x86 because that's what I worked with when I was working on my operating system, k4s, right? So, um, yeah, so let's go ahead and talk a little bit about how it works. Um, so I'm actually going to start not at the top of this definition file for the architecture, um, but I'm actually going to start down here. Where is it? So okay, let's start with this one, this little function here. So the basics of every CPU is that they have some kind of um, way to store intermediate values called registers. Um, so in k4s, in the k4s CPU, made up CPU, it doesn't actually exist, but I have an emulator for it that emulates this. We have 16 registers. Um, or wait, how many of these do we have? Yeah, 16. Sorry. um, so we have 16 registers. 12 of those are general purpose registers, and 4 are special registers. So, and all a register does is just holds a 64-bit value. Um, so, like a 64-bit number, right? That number can be an actual literal, number that is actually is represents itself, or it can be a pointer to a memory address containing a different value, and that address itself can be a pointer to something else, and et cetera, et cetera. Um, so, um, these are the registers that we have in k4s right now. We have RA through RL, which are your general purpose registers. Um, and then we have BP, SP, PC, and FL. So uh, BP and SP are used to keep track of the stack. So BP is a base pointer. It's the equivalent of RBP in x86 or 64. Um, it keeps track of where the base of the current stack frame is, and then stack frame is like it's used for calling functions. Um, so I guess I should go over what a stack is. So a stack in a CPU is it's really just like a chunk of memory. and then a pointer to wherever that chunk of memory ends, right? So typically your stack will be at the top of your memory, like the high end of your memory, and then it will grow downwards. Um, so so you have like I should really have a visual for this, but I'll leave links in the description to this kind of stuff if you want to learn more about how it works. Um, but essentially, you just have this register called SP, or the stack pointer, and what that does is that holds the address of the current top of the stack. So think of like a stack of papers, right? Like you can push a stack. You can push a paper or a page onto the top of the stack, and then you can pop a paper from the bottom of the stack, or sorry, from the top of the stack as well. You push onto the top, you pop onto the top. It's what we call a last in first out stack, or a LIFO stack, right? Um, so um, anyway, so we have the stack pointer, we have the base pointer, which is the location of the stack pointer at the time that we entered our current function. And this is useful because we can subtract the stack pointer at, we can, what was I going to say? Basically, the difference between a stack pointer and a base pointer gives us the number of bytes that our current function's local variables take up. This is all like getting into like how the compiler works and all that, but um, I'm not going to talk about the stack pointer anymore. Screw it. uh, it's just registers. So we have the PC, which is a program counter. Program counter is a pointer to the location in memory containing the current instruction being executed. So that's useful for like things like jumping, um, to new locations in memory, which is used for things like branching, um, like if you want to like do like an if statement in C, then that would use uh, a jump instruction, which in turn would update the program counter register, right? And then FL, which is just some CPU flags. So like these are flags for the current state of the CPU. Um, so things like if the last comparison was an equal comparison, or if it was a less than comparison, or if it was a greater than comparison, etc. Anyway, um, so the thing about k4s that I wanted to kind of touch on is that its machine code is actually procedurally generated. And what I mean by that is um, all I do, to generate the definitions of the machine code, like what, if I want to say I want to put RA here, then what byte in the machine code and like the binary does that correspond to? And I actually do that procedurally by just generating lists of everything that I want to have, and then it assigns a machine code instruction or machine code byte to it automatically. So if I wanted to like add an extra register, like I was thinking about adding a RZ register, which that's always 0, then I would now have 17 registers. And the RA would now have a different value. Array would now correspond to a different byte because RZ came to come before it, right? Um, so, and if I were to actually add this, I'm 99% certain this code would compile just fine. But the thing is yeah, it compiled just fine. All my assemblers and all my virtual machines are going to run perfectly fine. Even though I just added a brand new register into the entire thing. The thing is, if I were to remove this register and then not reassemble my, if I were to remove that register and then not reassemble my source code, my assembly source code, it would crash. The virtual machine would crash because that register no longer exists, which means RA now corresponds in the virtual machine to a different opcode, and and so it's all like not updated yet. So the advantage of this approach is that I can add and remove functionality to my architecture as I want to. But disadvantage is if I change anything at all, then it breaks compatibility with previously compiled code. So, um, yeah. But this is good for now because I'm still kind of prototyping this architecture. Um, so it allows me to kind of change things and not have to pull my hair out, updating every single constant. Um, Kind of generates them automatically. So, um, anyway, so but that's just as registers. And what I really want to talk about today is how the instructions work. So this right here, this giant valid instructions function is kind of the meat and potatoes of the architecture definition. So what this does is it generates. Um, it's really just it returns a vector, but allows me um, to add them as I want. Like I said, this is basically the definition of the entire architecture, and it's assembly language. Um, so I can list out every instruction that's possible here. I can list out its mnemonic. Um, I can list out what type of parameters it takes, what type of arguments it takes. So I can say, like for the NOP or no operation, it just does nothing. It doesn't take any arguments. So there's nothing following the NOP in the text on the same line. Um, and then I can list out what the valid operand sizes or argument sizes are for the operation. So obviously, because it has no arguments, it is unsized. Because there are no arguments. So, um, and that's the thing is like, so let me go over the language real fast. Um, this is an example program that I kind of created. It's also something I was just using to test out things. Um, and don't worry about this stuff at first, but take a look at these the start function, um, start label. So you can see that every instruction mnemonic is followed by in this case it's a Q, but it really could be a Q, a B, D, or W, and that is the instruction operand size. So it's kind of like in like AT&T syntax where you have like move Q or like call Q or like move B or stuff like that. I just put a space in between them in my sim language because that was easier to parse, honestly. Um, but what those stand for is B is byte, W is word, D is double word or D word, and Q is quad word or Q word. Um, so all that means is just a byte is 8 bits, a word is 16 bits, a double word is 32 bits, and a quad word is 64 bits. So that this specifies the excuse me. It specifies the what was I gonna say? The operand size. Like, am I calling something that is a keyword or am I calling something that's a byte or etc. You know what I mean? Um, so um, yeah. So in the valid operand sizes, I can have like byte, word, d word, or keyword. So now this correspond to B, W, D, or Q in the actual instruction itself in assembly language. So these are all instructions that k4s supports right now. I have the basics like NOP and halt. Um, I can move data around, and by move I really just mean copy. Um, that's what it typically means in assembly language. I don't know why they call it move. It really just means assign something to something else, or assign some value to some memory location, whether that is a register or that's actually a location in memory. I can do stack operations like pushing and popping to the stack. I actually added some kind of debug instructions called printy and print C, print I, print C. I call it printy because that's fun to say. All it does is that just prints in the virtual machine a number or a character value. I can use printc for printing strings. I can use printi for printing just numbers. If I want to inspect the value of a register or something, I can add that in there. So um, I can do very your typical arithmetic operations, like adding, subtracting, multiply, divide, modulo, which is just getting a remainder of an integer division. I can bitwise and, bitwise or, bitwise XOR, bit. I have comparison operations and branching operations like comp, CMP. I have jump for unconditionally jumping to an address. I have jump greater than, jump less than, jump of equal, and jump of not equal for conditionally jumping to a new address. I have call and I have ret for calling functions. These use the BP up, or actually they don't, but these basically use the stack to push a return address onto the stack and then pop it off the stack and jump to it. And then I can bitwise shift left and bitwise shift right. So those are literally all the instructions that k4s supports right now. It's kind of like right now it's kind of a reduced instruction set architecture. It's more like a RISC architecture. I kind of plan to keep it that way and do as much as I can with just these instructions. I mean, there's a lot that you can do with just these instructions, right? So it's very powerful, very kind of like reduced, very low amount of base instructions, but you can use these to build up more complex instructions. Like, as you can see, I already have stuff to, here, let me go ahead and recompile. And then see, I can print strings, I can print numbers, I can, I already have something to like print strings or like get the length of the string I've done. So there's a lot you can do with this. So and then this valid arg thing is just what types of arguments it can take. So where it's like a value, which a value can just be like a literal, it can be a label, it can be an address, it can just any literal value, or it could be an address, which an address needs to be resolved first. So that's important because they have different syntax in the assembly language and they work differently in the virtual machine. So the whether it's called with a value or whether it's called with an address is actually a different opcode in k4s. The different sizes of the arguments are not different opcodes. They're actually encoded with a different byte after the opcode byte. So, but the different types of arguments do have their distinct, opcode bytes. And I just made it that way just because it was simpler to, like I have enough room for all these instructions. Obviously, I think the maximum instruction is like, let's see here. Wait, what's the highest number we see here? It's like, yeah, that's actually part of the. It's like C4 or something, like hex C4, which is 196. Huh. Anyway, something like that. There aren't a lot of instructions, and so I have room to like afford to have all these and still have plenty of byte left. So, anyway, and then I generate the bytecodes, or I can generate the bytecodes for the or the opcodes. I use all those terms interchangeably. I don't know what the proper terminology is, but I can generate them all from this definition up here. So this literally just returns a static vector that I can just have, but this is always the same, right? This is just a definition of all the instructions. And then I can use this function to actually generate and, look up what the actual binary is for a specific invariant of an instruction, right? So, anyway, my voice is getting a little hoarse. I didn't get some water before this, I'm sorry. But I'm going to leave it there because this video is already getting pretty long. It's about 20 minutes long. So it's kind of me rambling about this architecture I've been building. I really didn't go over much of like how it actually works and how the assembler works and how the virtual machine works. But it's really just a lot of just parsing text and parsing bytes. And I use a nom crate for that. Nom crate's awesome. It took me a while to wrap my head around it, but now I have. It's really awesome. So anyway, that's gonna be it for today. Thank you all for watching. If you have any questions, leave them in the comments. If you have any comments, leave them in the comments. Make sure to like this video if you liked it. Hit subscribe if you really liked it and you want to see more about this architecture or more low level kind of like programming stuff. That's why I kind of want to make this channel around. So anyway, thank you all for watching. I'll see you next time. Peace out.